Okay, so we are now getting into talking about statistics, okay? So we're going to talk first about basically collecting data. And one of the big things with collecting data is what kind of method should you be using to collect it, and how do you avoid bias in the way that you collect your data so that way you're not getting inaccurate information. So there are three kinds of statistical studies. We have a survey, and that's where you go and you specifically ask people for information. So you're interacting with the respondents and you're specifically asking them questions and you're getting information from them. Observational study, that's the second one. That's the kind of case where you have no interaction with the respondents. You're simply either looking at data that's already been observed about them, or you're just specifically watching from a distance. And then finally, an experiment. That's where you're specifically taking control of a situation and you're breaking things into more than one group, a lot of times two groups, and you're saying, okay, does this one group act differently than this other group after they get a specific kind of treatment? And that's how you know it's an experiment. A lot of times you're using that to attest the effectiveness of something. So if we read these examples, we want to identify, is it an experiment, is it a survey, or is it an observational study? The National Highway Traffic Safety Administration conducts annual studies on driver seatbelt usage at a random selection of roadway sites in each state in the United States. To determine if seatbelt usage has increased, data are analyzed over 2 successive years. So what you're basically looking at is the NHTSA, I guess you would say, is watching if drivers are using their seatbelts. They're not asking the drivers if they're using their seatbelts. They're not breaking into 2 groups and giving them different treatments. They're simply just watching. This would be an example of an observational study. Okay, so they're looking at observed data or just watching themselves. B, people should brush their teeth at least twice a day for at least 2 to 3 minutes with each brushing. For a statistics class project, you ask a random number of students at your school questions concerning their toothbrushing activities. You are asking people what their responses are to a specific kind of, questions. That's why this is a survey. And by the way, generally we use sample surveys, so it's a sample of the population that you're asking the questions so you eventually could draw conclusions about the larger population. And then finally, letter C. Study determines whether taking an aspirin regularly helps prevent heart attacks. A large group of male physicians of comparable health were randomly assigned equally to taking an aspirin every second day or taking a placebo. After several years, the proportion of study participants who had suffered heart attacks in each group was compared. Okay, so the biggest thing here is that you are taking this group of male physicians and you're breaking them into 2 groups that was randomly assigned, taking an aspirin or taking a placebo. The fact that they have 2 separate groups getting different treatments, this is an example of an experiment. Are you just watching? Are you asking questions from your group? Are you breaking your group into 2 or more groups? That's how you know if it's a study, a survey, or an experiment. Number 2, data from a random sample of 50 students in a school district showed a positive relationship between reading score and shoe size. Can it be concluded that having bigger feet causes one to have a higher reading score? Explain your answer. Data from a sample was just showing a positive relationship. There was no experiment that was being done. So the answer is that no. Only experiments can determine a cause and effect relationship. Okay, so while observational studies and surveys can indicate a relationship, okay, is there some sort of a connection? Only an experiment where you're breaking people into 2 different groups and doing that analysis on those 2 groups and seeing if they come out to be different, that's the only kind that can determine a cause and effect relationship. So in addition to gathering your information in the right way, it's also important that when you gather your information, you're gathering it in a way that we would consider to be unbiased. Is the way that we're collecting data affecting the responses that we're getting? So you want to be trying to pick the largest sample, and you want to try to avoid picking from groups that have an investment in whatever you're analyzing. A survey completed at a large university asked 2,000 students to estimate the average number of hours they spend studying each week. Every 10th student entering the library was surveyed. That's good because that means it's random. Okay, 2,000 students, that's pretty big. The data showed that the mean number of hours students spent studying was 15.7 per week. Which characteristics of the survey could create a bias in the results? We are asking to analyze the average number of hours that people are spent studying, but we're asking people entering the library. What's the problem with that? Well, when you're entering the library, you're probably more likely to study. So the method of choosing the students who were surveyed, that's the problem in this particular survey. We have a large sample, okay? We have a large population, a large university, analyzing the data. Every 10th student was good. But the problem, again, is choosing people that are entering the library because, again, they're more likely to be studying for a longer period of time than if I were to ask from, let's say, the cafeteria or something. The yearbook staff has designed a survey to learn student opinions on how the yearbook can be improved for this year. If they want to distribute a survey to 100 students and obtain the most reliable data, they should survey every third student sent to the office. Okay, that's probably people who are getting in trouble, so you don't necessarily know if that's good. Every third student entering the library, again, that's one very specific group of people. Every third student entering the gym for the basketball game. Again, probably a lot of people that are invested in basketball, so that might not necessarily be the best group. Every third student arriving at the school in the morning, that's how you're going to get the most random sampling of people in this situation. So that's how you're going to get the best results to accurately reflect the entire population. Which survey is least likely to contain bias? Surveying a sample of people leaving a movie theater to determine which flavor of ice cream is the most popular. This is a good one because, again, movies, flavors of ice cream, not too much of an overlap. It's not like they're going to have one invested in the other. Members of the football team to determine the most watched TV sport. I would say it's probably likely football team, football. Surveying a sample of people leaving the library to determine the average number of books a person reads every year. Leaving the library, more likely to read books. Surveying a sample of people leaving the gym to determine the average number of hours they work out. Going to the gym, more likely to work out. So the best survey that you could have is number 1 in that situation. Number 6, a principal is concerned about the decline in the number of students who purchase food from the cafeteria. A survey was developed to assist the principal. The most appropriate method would be for the principal to randomly select 100 students from the junior class, the student directory, Algebra 2 classes, the students who are eating lunch during the 4th period in cafeteria. Okay, so the junior class, very specific. Okay, Algebra 2 classes, also pretty specific. Even though I know you have a little sophomores, little juniors, you're keeping like 2 very large populations, the freshmen and the seniors, out of it. Students eating lunch in 4th period, again, not everybody eats lunch, and you might get a good-ish sampling there, but it's not going to be the best. The student directory would be the best because you're going to get an equal number of all the different, ages and grades and all that kind of stuff. And again, people purchasing food from the cafeteria, these people clearly go to the lunch period during this cafeteria during this time, so they're going to have an investment. You want to try to have, again, the most random sample when you're selecting people for your survey. Okay, so normal distribution and z-scores. Okay, so it says the scores on, so normal distribution is basically when you see that bell curve. What the bell curve is supposed to be representing, imagine this like bar graph where the largest amount of bars or the highest bars are right there in the middle. You would say, okay, the mean is right here in the middle. Okay, as you work your way out from the mean, you have something called a standard deviation. You're either adding a standard deviation up or you're minusing a standard deviation down, and it's basically going to tell you how spread out your data is. Well, using the mean and the standard deviation, you can find out percentages that fall below a certain point, above a certain point, between 2 certain points, along with some stuff in the calculator to find out the exact probability of something occurring or the percentages in a specific situation. So it says the scores on a standardized test are normally distributed with a mean of 560. So in this situation, think of your bell curve with a mean of 560. Okay, it says, and a standard deviation of 75. Find the probability that a test picked at random will have a score larger than 720. Round your answers to the nearest thousandth. So 720 is to the right of 560. We want to find out what percentage have a score larger than 720. Okay, so what's going to happen is when we type this stuff in our calculator, you're going to need a lower, you're going to need an upper, You're going to need a mean. Now in your calculator, mean is going to look like this letter mu, and you're going to need a standard deviation, which is going to look like this O with like a little tail on it. Okay, so the mean is given to you, 560. The standard deviation is given to you, 75. You don't have to find any of that stuff out. The lower value in this case is 720 because you're trying to find out what's above 720. Because I'm not specifically given an upper value, it's not saying like 720 to 800, it's just saying larger than 720. Pick a really large number that's far to the right of 720 that you would assume to be almost like off of that scale, if you will. Maybe like 10,000, just to play it safe. What you're going to type all of this into in your calculator is normal CDF. Okay, so you go in your calculator, second variables button, second VARs, normal CDF. Okay, now in my calculator, I have to actually type them in this order, but yours might actually say lower, upper, mean, standard deviation. So I'm going to do 720, so that's my lower. My upper, like I said, do 10,000, million, do like a really big number that's to the right of 720. Mean is 560, standard deviation is 75. It has to be in that order. So when I do that, I get 0.016. It's saying round your answer to the nearest thousandth, so 3 decimals, so that's 0.016, or about 1.6% of scores will be larger than 720. Okay, so a very small amount. That's why it's kind of off on the edge of that bell curve. Number 2, find the probability that a completed test picked at random will have a score less than 500. So again, our mean is 560 right here in the middle. 500 is to the left of 560. We want to find out what are the probabilities that it goes less than 500. So again, we need a lower, an upper. Okay, we need our mean, and we need our standard deviation. So the lower value, that's going to be what's totally to the left of my shaded area. Since I don't actually have a value there, I could use 0. I don't know, to play it safe, I'll just use like negative 100. It really doesn't make a difference. You're still going to get the same answer. This time, my upper value is going to be 500, but my mean and my standard deviation are still going to be the same. Okay, so second variables, normal CDF. Make sure you don't use normal PDF. Negative 100, comma 500, comma 560, comma 75. This time this is a little higher. It says 0.212, so about 21.2% of scores will be below 500. Find the probability that a completed test picked at random will have a score between 500 and 600. So I have this right here, 500 to 600, so 560 is in the middle, 500 to 600. Okay, so this time I actually do have a lower value, 500. I have an upper value, which is 600. My mean is 560, and my standard deviation is 75. And then I just go back and I once again do normal CDF. So second variables, normal CDF. My lower is 500, my upper is 600, 560, and 75. So this comes out to be 0.491. So we're going to eventually start getting into drawing conclusions with our information. So I'm going to use an example where we have to draw a conclusion based on a mean and a standard deviation and things like that. If you wanted to, you could practice these for some extra practice. But I want to go down to the last portion of this question. So it says a particular medical procedure has a cost that is approximately normally distributed with a mean of 19,800. Okay. And a standard deviation of 2,900. For a randomly selected patient, right here, suppose that a patient is charged $24,900 for the procedure. The patient is reported as saying, I've been charged an outrageous amount. How justified is this comment? Use probability to support your answer. Okay, so basically what happens is with this normal distribution, if you go out 2 standard deviations in each direction, to the left and to the right of the mean, you make what we call a normal interval, which I'll eventually refer to as a confidence interval. So if my mean is 19,800, to make my confidence interval, I'm going to do mean minus 2 standard deviations, mean plus 2 standard deviation. And this is going to give me a normal window for, in this case, values for these procedures. So my mean is 19,800 minus 2 times 2,900, and 19,800 plus 2 times 2,900. Okay, so 19,800 minus 2 times 2,900. So that's a lower bound of 14,000. Okay. And that's an upper bound of 25,600. Okay. Scores that fall in this range between 14,000 and 25,600, even though I know that this might be on the higher side of things, it still falls within that normal window. So this lady is actually not justified in saying she's been charged an outrageous amount. She's actually having a value that falls within that range. Okay, so you would say since 24,900 falls within the normal interval, her claim is not justified. Okay, she is not paying an outrageous amount. Okay, what we're going to end up looking at in the next lesson is if it falls above or it falls below, but the main idea is if something falls within the normal window, it's a normal value. She's claiming she was charged an abnormal amount. She was not. Okay, so as I was mentioning at the end of the last lesson, we're going to start creating something that I like to refer to as the normal interval. What it's really intended to be called is the 95% confidence interval. Okay, so based on having a lot of times a normal distribution, that when you find the values that fall between two standard deviations, so in the case we were talking about 14,000 to 25,600, this represents 95% of the normal values in this situation. Something that falls outside of that is considered an abnormal value. Okay, so what we're going to do is we're going to create this margin of error, and then we're going to draw conclusions from that. Okay, whether it falls within or outside, something like that. All right, so to create your margin of error, to create your confidence interval or your normal interval, you should know that technically if somebody asks you just for margin of error, we're talking about 2 standard deviations. Okay, so we should really put plus or minus 2 standard deviations. You're going to put 2 standard deviations added to the mean, 2 standard deviations minus from the mean. So if you're actually given the mean and the standard deviation, that's what you do. You take mean plus 2 standard deviations, mean minus 2 standard deviations, and you make your normal window, and then you see if based on the problem something falls within the normal range or outside of it. If you're given a situation where it's a proportion, like a percentage of people in a population, you need to calculate your standard deviation using this formula, the square root of p times 1 minus p divided by n. With that confidence interval, you're going to do p minus 2 standard deviations, p plus 2 standard deviations, and that's how you're going to be able to figure out what's your normal window in that situation. So if you take a look at example number 1, it says Elizabeth waited for 6 minutes to drive through at her favorite fast food restaurant the last time she visited. She was upset about having to wait long and notified the manager. The manager assured her that her experience was unusual and it would not happen again. A study of customers commissioned by the restaurant found an approximately normal distribution of results. The mean wait time, so the mean, which is our x bar, was 226 seconds. The standard deviation was 38 seconds. So this is the first situation we have. We have the mean and the standard deviation, so we're going to make that confidence interval, that 95% confidence interval, that normal window. So to do that, you're going to do mean minus 2 standard deviations, mean plus 2 standard deviations, and you're going to see what that window comes out to be. So 226 minus 2 times 38, and 226 plus 2 times 38. Okay, 226 minus 2 times 38 is 150. 226 plus 2 times 38 is 302. Okay? So a normal time that people wait is 150 to 302. That's a normal wait time. Is anything between 150 and 302. So now Elizabeth waited for 6 minutes. Obviously 6 is not in that window, but be careful. 6 minutes, and these are talking about seconds. I have to do 6 times 60. She really waited for 360 seconds. Was she right to complain? Well, the answer is yes. Since 360 is above the normal window, or the normal interval, it is true that her wait was unusually long. Okay, a normal wait time would be between 150 and 302. Okay, take a look at the second example. A school newspaper at a large high school claimed that 75% of seniors, so your claim is 0.75, are in favor of assigned parking spaces. A random sample of 200 seniors were surveyed, and 120 of them said they were in favor of assigned parking spaces. Given these data and a 95% level of confidence, is the school newspaper justified in their claim? So we have to figure out what is our confidence interval for this situation, and does 0.75 fall in that interval? That's what happens when you have a claim. So the question is, what is P? This is one of those ones with a proportion because you're talking about percentages. 120 out of the 200 students in that school, so 120 over 200, is 60%. So 0.6 said that they were in favor of assigned parking spaces. But again, there's a margin of error when you're not asking everyone, so we need to figure out what's a normal window. So to figure out the standard deviation, we're going to use that formula that I had mentioned on the bottom of that page right here. The square root of P, 1 minus P divided by N. So the square root of P times 1 minus P divided by N. So the square root of 0.6 times 1 minus 0.6 divided by N, that's the sample size, 200. So square root of 0.6 times 4 divided by 200 comes out to be 0.0, let's just do 0.03. Okay, so to make our confidence interval now, this is we're dealing with a mean proportion instead of an actual mean itself. What we're going to do is we're going to do P minus 2 standard deviations, P plus 2 standard deviations, and you're going to use that to create your confidence interval. So 0.6 minus 2 times 0.03 and 0.6 plus 2 times 0.03. Minus 2 times 0.03 comes out to be 0.54, and 0.6 plus 2 times 0.03 comes out to be 0.66. Okay, so the amount of students that actually want assigned parking spaces is between 54% and 66%. In this particular case, the claim was 0.75, so you'd say, no, 0.75 is not in the confidence interval, so the newspaper is not justified in their claim. Okay, so those are the two main kinds you're going to be looking at. A situation where you are given the mean and standard deviation, and a situation where you have a percentage, so you deal with proportions. You make a confidence interval, and you see if your value falls within it or outside of it, and you use that to draw a conclusion about what's going on in that situation.